Hi, my name is Mikhail Prisyanov, and today I present to you our work called Learning of Population Dynamics Inverse Optimization meets JKO scheme. So, what the problem we are trying to solve? We are trying to solve the problem of population dynamics. What is the problem? The problem is that we have some measure that changes over time, and we are given samples that are uncorrelated over time. This is very practical problem. For example, in single cells, some cells can be, they live, then we measure this cell and it dies. So this trajectory just abrupts over in some time point. And for example, some measure is born at some time and then it leaves, and we have some uncorrelated samples, and we want to predict the evolution of these points. And for example, we want to measure in some, for example, we have 0 point and 1 point, and we want to obtain some measure in between these time points. So what the assumption we have? We have that this evolution of rho is just the decreasing of f in space of measures. So this evolution of rho is the same as just going to minimum of some functional f, and we want to restore this functional f. And here is the mathematical equation of this evolution. It is continuous in time, and here is the discrete in time counterpart of this equation. It says that if tau goes to 0, we restore this continuous time. And this is the just implicit Euler scheme. What does it mean? It's like j at rho k is minus gradient of j at rho k plus 1, and this is the equivalent formulation for this. Here's the related works that modulate the dynamics with gradient flows. Here's the first work. It was in 2022, and the idea is to simulate the whole trajectory with JKO scheme. They explicitly solved the scheme with some neural network. It was very hard and long in time, and you need to propagate through the whole trajectory to make gradient update of j theta. They also have only limited parameterization, since they use only potential energy, and they also use the idea that the mapping is the gradient of convex function. To model the convex function in practice, you need to use ICNNs. ICNNs are very restrictive, and this was the first attempt to model the population dynamics. It was good in this time, but not very practical. The second approach is JKO star. It was NeoRIPS oral on 2024, and they decided to replace this explicit minimization with the first order conditions. What does it mean? It means that we take the gradient of this equation into 0, and then obtain some analytical solutions for this parameterization. What is the drawbacks of this approach? That you need to compute the ground truth plans, optimal transfer plans. This doesn't mean that the algorithm is not end-to-end. So in the beginning of training, you pre-compute it, and you cannot adjust it during train. And it also works poorly when we have large dimension and a lot of points. And when we trying to run it in our resources, we obtained out of the memory, so it has some drawbacks. And moreover, there is only constraint to such parameterization, and our approach quite general. It works for every functional j. So what is the idea? The idea, we have assumption that this trajectory came from some JKO steps with known j star, and we want to restore this functional. So here is some prediction with single step of JKO with unknown j star. Here's our approximation with neural network j theta. And here's the values of j theta at these different points. And by minimizing this gap, we force our j theta restore to the ground truth trajectory. So, yeah, this is the whole idea of our method: just minimize this gap and restore ground truth trajectory. These some details. We replace distance with minimizing this distance not over row but over mappings, and this is the final loss. We have theory that says if our potential, if we have energy only with potential term, and we can solve the internal problem arbitrarily well, and our V is convex, strongly convex, we can restore the ground truth functional from the points. Here's the example in on single cell data in 5D where SOTA, and here's just examples of on synthetic benchmark of restoring the ground truth potential energy. So here is the level curves of V, and what types of points do we have? On synthetic, we just sample uniformly on this square, and then make the single step with this equation, and we have 5 timestamps, and only by points we was able to restore the ground truth functional. So you can see just by points we can restore the function that gives this evolution. So thank you, that's all.